Proof by induction. Why do we need induction? Many mathematical statements claim that a pattern or rule works for every positive integer, not just the first few that we can check. For example, the sum of the first n integers is n plus 1 divided by 2. Checking for n equals 1, 2, 3, 4, and so on might suggest that it's true, but that isn't a proof. It's inductive reasoning based on observation. To prove it for all positive integers, we use mathematical induction, a formal method that converts a pattern observed in small cases into a logically valid proof for every integer case. The idea behind induction, and I may be a bit repetitive about this in this introduction. Think of mathematical induction as a domino effect or a ladder climb. To make all the dominoes fall, you only need to knock over the first domino, that's called the base case. Ensure that if one domino falls, it knocks over the next one, the inductive step. You've got the idea, and you could always look at a YouTube video of things that people have set up with the domino effect. You knock the first one over, and then that one knocks over the second, knocks over the third, and so on. Similarly, to climb an infinitely tall ladder, you must be able to reach the first rung, know that from any rung, you can always reach the next one. So it's very similar to the domino, but those two pictures give you a good idea of how induction works. If both conditions are satisfied, that is, the first rung and then every subsequent one, you can reach any rung or prove the statement for all n. So we have the principle of mathematical induction. Now, there are different things that we can prove with induction, and the algebra will take a different form, but the actual process of doing a proof by induction is always the same. To prove that a statement P of n is true for all positive integers, we need a base case, which is like the first domino. Prove that P of 1 is true. Sometimes the first case starts at n equals 0 or n equals 2, depending on the problem. But the first one that you can show is true is the base case. Then we have the inductive step. Assume that P of k is true for some arbitrary integer k greater than or equal to 1, or greater than or equal to the number of the base case. This assumption is called the induction hypothesis. Then we have the inductive conclusion. Use the assumption that P of k is true to prove that P of k plus 1 is also true. Therefore, since the statement works for the first case, the base case, and each case leads to the next, P of n is true for all n belonging to z. And just pause for a moment and think about the domino. You push over the first one, the base case, and then each one knocks over the next one. And if you had an infinite number of dominoes, that would just keep going forever. Common analogies, we've seen these with the ladder. You can reach the first rung. From any rung, you can reach the next one. The domino chain, you can topple the first domino. Each domino knocks over the next one. And then we have the logical chain, which is how we're going to do most of these proofs, where P of 1, or at least P of the first case, is true. And if it's true for some n equals k, it is implied for k plus 1. And that is, it works for this case, and therefore it works for the next case. So that's like the dominoes. If these two conditions are met, the truth propagates infinitely. Typical forms of induction problems. You can use induction to prove statements involving algebraic formulas. For example, the sum of the first n integers is n plus 1 divided by 2. Divisibility. For example, 4 to the n minus 1 is divisible by 3. Inequalities. For example, 2 to the n is greater than n squared for all n greater than or equal to 5. So the base case there would be 5. Series and sums. For example, the sum of the first n cubes is n plus 1 over 2 all squared. So that's the same sort of thing as an algebraic formula, really. I don't know why I put it down as a separate case. Recursive definitions, for example, results involving Fibonacci numbers. Sometimes these are just very slightly different in the algebra, and we'll see that in the examples that follow. However, the overall structure is the same. And this is a bit repetitive. Structure of a formal induction proof, but I really want you to get this idea. That's why I'm repeating myself. Each induction proof follows the same logical outline. Base case, induction hypothesis, inductive step, and conclusion. I won't go through all the stuff over here because we have talked about it before, but it's really important that you get this idea. Why induction works, the logic behind it. The process is a direct application of a chain of implications. P of 1. P of 1 and P of 1 implying P of 2. And that implies P of 2, and then you can see that's going to go on P of 1 and P of 1, P of 2 and P of 2 implying P of 3. So that is where the ladder or the domino analogy comes in. In other words, if we know this one works and we know the next one works, then that one works. And if we know the next one works, then that one works. And that's what that's really saying. Thus, proving the base and the link guarantees the truth of all subsequent cases.